In this video, we're going to describe what is the significance of the gradient of a given function outside of just its use with the directional derivative. So first significance of the gradient is going to be that the maximum value of the directional derivative at a given point is the magnitude of the gradient at that point. The direction in which this occurs is the same as the gradient. Now, the proof of this is going to be relatively straightforward. So if we consider the directional derivative of a function at a given point, we defined in the last video that that is equal to the gradient vector dotted with our given unit vector. Now, from back in a previous chapter, if we have the dot product of two vectors, that is the same as saying, let's take the magnitude of these two vectors times magnitude of u times the cosine of the angle in between them. Now, right away, one of these terms we can get rid of immediately because the magnitude of a unit vector is guaranteed to be 1. As a result, the expression that we get is going to be that the directional derivative is going to be equal to the magnitude of the gradient vector times the cosine of theta. Now, when it comes to the cosine of theta, the maximum value is 1, and it occurs at theta equals 0, or 2 pi, or 4 pi, or 188 pi, but it's all the same because all of those angles are pointing in the same direction. So this means that the angle between the direction vector and the gradient vector has to be 0. Well, that means they're pointing in the same direction. So, given that the maximum value of this quantity is equal to 1, that means that the maximum value of the directional derivative is going to be equal to the magnitude of the gradient vector times 1, which takes us to the statement, the maximum value of the directional derivative is the gradient vector, and the direction in which this occurs is the same as the gradient. Now, the other thing that that does for us is that means that the gradient vector defines the path of steepest ascent. Now, the path of steepest ascent, when we talk about ascending things, we're talking about rising or going up something. The steepest ascent means the largest value of the slope that takes us there. Now, with that in mind, the largest value of the gradient vector is always going, the largest value of the directional derivative, or that path of steepest ascent, is always going to be based off of the gradient vector. That also means that if we wanted to do the quickest descent, we would just point ourselves in the opposite direction of the gradient vector. And finally, the gradient vector is orthogonal to a level curve. Or rather, the level curves and the gradient vector will always be orthogonal to one another. Now, reason being, a level curve describes a situation in which the slope is essentially 0, or the value of the directional derivative is 0. On a level curve, the value of z is not supposed to be changing, therefore its directional derivative would be 0. Well, the only way that that's possible is if this quantity that we had right back here is equal to 0. Well, this magnitude isn't necessarily going to be equal to 0, so we would have to rely on the cosine of theta being 0. So we want the directional derivative to be equal to 0, and that's going to be equal to the magnitude of f evaluated at a given point times the cosine of theta. We can't rely on the gradient being equal to 0, so really what we're saying is that the cosine of theta is equal to 0. Or more specifically, if the dot product between two vectors is equal to 0, that guarantees that those things are going to be orthogonal to one another. So with cosine of theta being equal to 0, that means that theta is going to be equal to pi over 2. Therefore, these things are going to be orthogonal to each other. I think a real-world example is probably in order here.